digital screens process binary data, yet they produce continuous images. This creates a fundamental tension between discrete electrical signals and analog visual perception. Understanding this conversion requires examining how electronic components bridge the gap between abstract information and physical light emission. Now we examine how this conversion occurs physically. The process begins with addressing individual pixels within a grid structure. Each unit receives specific commands to control its state. We will trace these signals from the controller chip through to the final light output mechanism. To understand how a screen creates an image, we must first confront the fundamental disconnect between digital data and physical light. Your device stores information as binary code, which consists of discrete zeros and ones that represent distinct states. In contrast, a display panel requires continuous analog voltage signals to control the intensity of individual pixels. This creates an immediate translation challenge, because a stream of integers cannot directly drive the smooth gradients required for color. Imagine a digital file containing the number 127. This value must be converted into a specific electrical current that determines brightness. The system transforms these discrete binary values into continuous voltage curves, where higher numbers correspond to stronger electrical flow. Without this conversion, the screen would only produce dark on or off states rather than the nuanced tones we perceive as images. This discretization process is the critical bridge that allows digital instructions to manifest as visible light output. Once these analog signals are established, they must be routed to specific locations within the display matrix. We will now examine how this electrical data maps onto the physical structure of the screen itself. Pause 0.8. To understand how a screen constructs an image from binary signals, we must first examine the physical architecture of its display surface. The screen is organized as a rigid matrix, where each individual light emitter functions as an addressable unit known as a pixel. This grid operates on a row-column intersection logic that allows precise control over specific locations without affecting neighboring elements. Imagine a coordinate system where horizontal lines represent rows and vertical lines represent columns, with every pixel situated at their unique crossing point. When the display controller activates a single row while simultaneously selecting a column, an electrical signal reaches only the pixel located at that exact intersection. This mechanism ensures the data intended for one specific location does not inadvertently alter the state of adjacent pixels within the same matrix. For example, if we wish to illuminate a red dot in the center of the screen, the system targets the precise row and column coordinates corresponding to that central position. By rapidly cycling through these addressable points across the entire grid, the display controller constructs complex visual patterns from simple binary inputs. This spatial organization forms the foundational framework upon which color information is subsequently layered for full color image rendering. Pause 0.8. To understand how screens generate color, we must examine the additive mixing of light at the subpixel level. Each pixel on a display is physically composed of 3 distinct emitters, one red, one green, and one blue. These primary colors do not mix through pigments but through the direct addition of luminous intensity from each source. When all 3 subpixels emit light at maximum brightness simultaneously, our visual system integrates them into a single perception of white. Conversely, varying the relative intensities allows for the creation of millions of intermediate hues across the visible spectrum. This precise modulation of red, green, and blue emitters forms the fundamental mechanism behind every color you see on screen. Pause 0.8. The process begins with the driver integrated circuits, acting as essential translation intermediaries between digital logic commands and physical power delivery. These specialized chips receive binary data from the main controller and convert it into precise analog voltage levels required by each pixel subunit. For example, a gate line signal might activate an entire row of pixels simultaneously while source lines deliver specific voltages to individual columns. This two-step addressing system ensures that only targeted pixels change state without affecting their neighbors in adjacent rows or columns. The driver ICs regulate current flow through thin film transistors, which function as microscopic switches controlling liquid crystal alignment. Without this precise voltage regulation, the display would produce inconsistent brightness levels and color inaccuracies across the screen surface. Pause 0.8 to understand how a screen turns signals into images. We must examine the physics of light modulation within liquid crystal displays. The core mechanism relies on controlling the polarization state of backlight photons as they pass through a layer of liquid crystals. In their resting state, these molecules are aligned in a helical structure that rotates the plane of polarized light by 90 degrees. This rotation allows light to pass through the second polarizing filter and reach your eye, creating a bright pixel. When an electric field is applied via the driver circuitry, the liquid crystal molecules reorient themselves perpendicular to the glass substrates. In this aligned state, they cease rotating the polarization of incoming light, causing it to be blocked by the second polar filter. This binary control between twisted and untwisted states effectively modulates brightness for each individual pixel on the display matrix. The result is a precise image formed by selectively blocking or transmitting backlight across millions of microscopic subpixels. While this electro-optical modulation is highly efficient, it represents a fundamentally different approach than self-emissive technologies. Pause 0.8 in an OLED display. Each pixel functions as its own light source through a process called electroluminescence. When voltage is applied across the organic layers, electrons and holes are injected from opposite electrodes into the emissive material. These charge carriers migrate toward the center of the layer, where they meet and recombine to form an excited state known as an exciton. The relaxation of this exciton releases energy in the form of a photon, with the color determined by the specific bandgap of the organic molecule used. For example, a blue-emitting material has a wider bandgap that requires higher energy transitions compared to red or green variants. This direct conversion of electrical current into light eliminates the need for a backlight found in LCD technology. The precise control over individual pixel brightness allows for true blacks and high contrast ratios in the final image. Now that we understand how light is generated at the pixel level, we must examine how these pixels are refreshed over time to maintain a stable image. Pause 0.8. To understand how a screen turns signals into images, we must examine the temporal refresh cycle that sustains visual continuity. The display controller sends sequential frames of static data to the pixel matrix at high frequency, typically 60 times per second or more. Each frame represents a complete snapshot of the image state, which remains illuminated for a brief duration before being replaced by the next update. This rapid succession creates an illusion of motion, because the human visual system retains each image momentarily on the retina through persistence of vision. For instance, if you observe a spinning fan blade in low light, your eye blends individual positions into a continuous blur rather than distinct segments. Similarly, when frames flash faster than the critical flicker fusion threshold, the brain integrates them into smooth movement instead of separate pictures. If the refresh rate drops below this threshold, you will perceive flickering or stuttering motion as the gaps between updates become noticeable to your perception. This mechanism ensures that digital signals translate seamlessly into coherent visual experiences without requiring constant physical changes in the display hardware. Pause 0.8. The screen converts binary data into visible images through layered physical processes. Digital signals drive electrical currents that modulate light emission or transmission at the pixel level.